The Bloomington and Normal Water Reclamation District was organized under the authority of the Illinois Sanitary District and Sewage Disposal Act of 1917. The district is operated as a separate governmental entity, much like a city or a school district, and is governed by 3 trustees appointed by the McLean County Board. The district's mission is to recycle wastewater safely, efficiently, and economically to improve quality of life, maintain public health, and protect the environment in areas in which it serves. The Bloomington Normal Water Reclamation District relies on natural processes to clean and purify dirty water before it's returned back to the water cycle. Using biological and physical treatment methods, skilled and trained staff at BNWRD produce high-quality effluent, which is then discharged to Sugar Creek. The district's service area includes Bloomington, Normal, Downs, and the Crestwick subdivision. In addition to these urban areas, BNWRD also accepts wastewater from rural areas within McLean County. The district owns, operates, and maintains the major interceptor sewers which convey residential, commercial, industrial, and stormwater to 2 separate wastewater treatment facilities, the west and southeast plants. It also operates a combined sewer overflow storage lagoon, a preliminary grit removal system, and a 240-acre tree farm near Shirley, Illinois for biosolids application. The West Plant has been in operation since June 7, 1928. In order to keep pace with population growth and ever-increasing stream water quality standards, numerous plant expansions have been undertaken by the district over the years. Despite the numerous additions, however, some elements of the plant are virtually unchanged since the 1920s. The West Plant has 3 parallel secondary treatment processes, which can process an average of 22.5 million gallons per day and a maximum of 45 million gallons per day. A wet weather or excess flow facility on site can provide preliminary sedimentation to an additional 42 million gallons per day. On average, the West Plant treats 70% of all wastewater generated in the Bloomington Normal Water Reclamation District service area. Roughly 99.99% of the wastewater treated is water, and only 0.01% is personal waste. Less than 10% of the wastewater treatment is from industry, and approximately 1/3 is rainwater. The journey from dirty water to clean water begins at the source of use. Wastewater is conveyed to the treatment plant via a network of sewers called the collection system. Local municipalities, including the Town of Normal and City of Bloomington, own the main sewers, which receive flow from the smaller branch and lateral sewers connected to homes and industries. The district owns the large interceptor pipes, which receive flow from the mains. As wastewater enters the treatment plant from the collection system, it first passes through preliminary treatment to remove large debris and inorganic material. Mechanical bar screens capture debris and move the inert materials to a dumpster to protect downstream equipment from becoming damaged. The grit chamber uses an auger and pump to remove the inorganic solids like sand, grit, and gravel, which is then hauled to a landfill. The West Plant then splits into 2 different treatment trains, the original Plant 1 trickling filter process and Plant 3 activated sludge process. On average, 60% of the flow is treated at Plant 1 and the other 40% at Plant 3. After receiving preliminary treatment, flow is pumped to 4 center feed primary clarifiers. The primary clarifiers are 10 feet deep and are designed to settle out solids, which are then pumped to a primary digester for further treatment. The process reduces suspended solids and the biological oxygen demand loading on the downstream treatment, which helps improve removal rates. The fixed film process is a biological process that converts dissolved solids into settable solids. The process contains 2 stages. The first stage, trickling filters, use rocks 2 to 3 inches in size as a surface for bacteria, called the zoogliomass, to become attached. This is an aerobic process that removes a large portion of the carbonaceous oxygen demand. The rock media is exactly the same as it was when the plant was first placed online. The second stage is called the biotowers or nitrification towers. Instead of a rock media, the biotowers use a synthetic plastic media which provides a much larger surface area for bacteria to grow on. This is important because the organisms which metabolize the organic constituents utilize the surface of the media as a place of attachment. The more area for the biological growth to attach, the better the treatment. In the biotowers, a process called nitrification occurs. This converts the ammonia nitrogen to nitrate nitrogen through the use of ammonia oxidizing bacteria and nitrite oxidizing bacteria. The fixed film process is impacted by ambient air temperatures. Treatment efficiencies are superior in the summer compared to winter months. After the biological treatment, flow enters the secondary clarification tanks. Biomass, or microbes, and the solids they produce settle to the bottom and are removed to the solids handling facility, where they are thickened before being pumped on to anaerobic digestion. After clarification, deep bed tertiary sand filters capture any remaining solids as the water passes through filtration media. Ultraviolet disinfection, using light at a wavelength of 253 nanometers, destroys any pathogenic bacteria or viruses by rupturing cell walls and damaging DNA structure, which prevents reproduction. The highly treated water is then returned to our local stream, which is Sugar Creek in the Salt Creek of Sangamon watershed. Built in 1977, the activated sludge plant can treat up to 16.5 million gallons per day. Unlike Plant 1, Plant 3 does not utilize primary clarification. After receiving preliminary treatment, wastewater flows into aeration tanks. Large blowers supply the air, which mixes the contents and helps maintain desirable living conditions for billions of protozoa and bacteria, referred to as microorganisms. The aeration tanks are the heart of this process. Microorganisms convert organic material in the wastewater into microbial biomass and carbon dioxide gas. Raw sewage has a high oxygen demand and contains ammonia, which is harmful to aquatic life. These microorganisms remove the biological oxygen demand and ammonia by feeding on organic waste in the sewage. The water then moves into secondary clarifiers, where the solids settle to the bottom of the tank. Microorganisms in the aeration tanks reproduce as they feed on wastes. This requires roughly 20% of these solids to be removed from the process every day and sent to a solids handling facility, while the rest is returned to the aeration tanks to break down the organic material. After biological treatment, treated wastewater goes through tertiary filtration, which uses low-head traveling bridge filters with dual media. Anthracite on top of sand captures the suspended solids. UV disinfection follows before the treated water is returned to our local stream, Sugar Creek in the Salt Creek of Sangamon watershed. Wastewater treatment requires a high demand for power consumption. The district achieves considerable efficiency with its use of the Supervisory Control and Data Acquisition System, referred to as SCADA, which monitors and controls a large portion of the West plant process. Small computers called programmable logic controllers allow for automation of processes based on operator inputs and field sensing devices. A fiber optic ring collects the data from the remote PLCs and reports back to a master station where staff can control pumps, gates, valves, and other components. Data is continually trended and analyzed to allow for quick diagnosis of potential problems as well as optimization. Alarm monitoring software alerts operations staff of any issues during non-business hours. Staff can easily access the plant computer system remotely and many times address the alarms from home. The district operations and laboratory staff regularly inspect and evaluate environmental conditions of the receiving stream as well as throughout each plant process to ensure compliance with state and federal water quality standards.
you.